Laplace posed this problem in the year 1812. Today we call it Laplace's law of succession. This idea was to have an entirely modern cast to it, some 150, 80 years later. This is our next application. The picture on your screen is that of the Great Pyramid of Cheops, constructed about 2580 BC. And ever since then, it has continued to inspire, to beguile, to cause wonder in all its beholders. The great financial crash of 2008 caused enormous turmoil in world financial markets. And in that turmoil, companies large and small were swept away in the rubble. A large-scale casualty was the venerable firm Lehman Brothers, which, after 150 years of existence, crumbled in that collapse. The evolutionary process of natural selection articulated by Darwin has seen the emergence of various species on the earth. Homo sapiens, in particular, emerged out of Africa approximately 200,000 years ago and continues to populate the planet. Space exploration began in earnest in the space race of the 1960s. The International Space Station, shown in your picture, was launched about 1998 and has been continuously inhabited since then. Military coups have troubled the world's history from times immemorial. The cartoon on your screen shows Napoleon Bonaparte trampling over egalite, freedom, when he takes over France in the early part of the 19th century. Of course, these kinds of events repeat and recur again and again in our history, and they're not at all uncommon in the 21st century, where a military coup or a junta takes control of a country with various reasons, inevitably with a promise to restore normal functioning shortly, but then the military power continues unabated for a period of time. What do all these examples and these images have in common? If we abstract out a key idea, it is that of a phenomenon which crops up into existence at some point in time and exists for a certain period of time before it vanishes. The Great Pyramid of Cheops, constructed about 2580 BC and lasting for, well, we don't know when, how long. The space station, launched in 1998, has a lifetime of some time in the future. A firm, a startup, a company, launched at some time in the past and has in existence a lifetime of some duration. In all these cases, at the current moment, we observe that phenomenon. What we have seen is that the phenomenon has existed for a certain period of time, an elapsed time, let's call that R. And the phenomenon is going to continue to exist for a certain additional period of time till its lifetime is done. It's a future time for the phenomenon. A question, whimsical to be sure, that one might pose is the following. At the point of time where we observe this phenomenon, say the Great Pyramid of Cheops, the phenomenon has been in existence for a certain amount of time. So the Pyramid of Cheops has been in existence for about 4,600 years. So the phenomenon has continued unabated. It has lived for, let us say, little r days. Given that the phenomenon has existed for r days, what can we say about the chance that it will persist for an additional s days? This looks worse than tenuous. It's not at all clear what the underlying sample space for such an experiment might be. What does the distribution of the lifetime of the phenomenon? Well, we don't know. And the varied examples I've given you show very different kinds of phenomena. we don't even have the beginnings of a model for lifetime distributions. Could we make any progress? Well, here is an idea. This was articulated by the Princeton astrophysicist Richard Gott in 1993, and the idea was to posit a principle for future time given a certain elapsed time. And Gott's idea is what we could today call the Copernican Principle, and it can be encapsulated very snappily, in a very memorable fashion, by saying that the point of observation is not special. Now, what does that mean, and where does Copernicus come into the picture? Let me take you back to about 2 millennia, to about 100 AD, and the world that was seen by Claudius Ptolemy. Ptolemy was a mathematician, an astrographer, an astronomer, sometime writer and poet, and by detailed and careful observations, he figured out the particular orbits of each celestial body around the Earth. This is now what we call the Ptolemaic Universe. The orbits that each body takes around the Earth are quite complex. They form cycles, epicycles, epicycles upon epicycles, as seen in a figure. But if one is careful, one can very painstakingly construct individual orbits for every celestial body as it circumnavigates the Earth. Now, this model had substantial enduring power. This model of the universe persisted for about 1,300 years, until Nicholas Copernicus, in about the early part of the 16th century, around 1510, said, the model is not accurate. Copernicus, by dint of observation, posited that a proper model would be to place the sun at the center of the known universe. And soon after Copernicus postulated this revolutionary, reactionary idea, Kepler, about 80 years later, by dint of careful observation, figured out that every celestial object in the skies has beautifully regular geometric orbits around the sun. And about 100 years later, Isaac Newton, through the discovery of universal gravitation, discovered that all of this could be described by a very simple mechanical experiment. By one equation, force is equal to mass times acceleration, and this gives you all the elliptical orbits that we are familiar with today. What does this have to do with our problem of the existence of a phenomenon? Well, here's the key principle, the key idea that Copernicus articulated, which overturned 1,300 years of Ptolemaic dogma, was that the Earth was not the center of the universe, but the sun was. Revolutionary, reactionary, dangerous, but accurate. His idea was, in a large sense, a huge blow to our collective egos. We could paraphrase what he said by saying, we do not have a special place in the universe. We are not special. Now, if we take this principle and apply it to our setting of a phenomenon, the Copernican principle says the observation point is not special. What that could say is that the observation point is just as likely to be in the first quartile of the existence of the phenomenon as in the last quartile of the existence of the phenomenon. We should make haste to understand that this is an assumption. A naive, blind utilization of such an assumption could lead to ridiculous results. But let us take this assumption, which on face value doesn't seem unexceptionable, at least perhaps in some circumstances, which are not understandably well specified yet. But if we take this principle to heart, what does this say? It says, effectively, that a Laplacian law of succession is an operation. Look at the Laplacian equation on the top right. What does it say? Right. We recall the experiment was drawing balls repeatedly from a randomly selected urn. Given that our red balls have been drawn in succession, the chance that S subsequent balls drawn are red was approximately, when the urns are very large in number, about R plus 1 divided by S plus R plus 1. If we posit a model of Copernican uncertainty to the observation point, then an approximately equivalent Laplacian prior might posit that the conditional probability, whatever the underlying probability space is, of the future duration being at least S, given that R days have elapsed in the phenomenon's existence, is about R over S plus R. You should compare the Copernican principle as we've outlined it with the Laplacian model for the Laplace's law of succession. And we realize this is essentially articulating the same principle of Laplacian uncertainty. Now, of course, you could cavil at this kind of touchy-feely, loosey-goosey application of probabilities when it's not even clear what the underlying sample space for the experiment is. But let us see where this kind of modeling format or assumption leads us. Various diverting calculations can be made once we make such an assumption. And let me show you a couple. So to begin, what can we say about the probability that the future time for this phenomenon, the future existence, lies between R over 39 and 39 times R, given that the elapsed time is R days? Now, I can immediately write an equation down, but this would probably require a little bit of thought. Let's begin with the first term on the right, the probability that the future time exceeds R over 39, given that the elapsed time is little r days. Now, if the future time exceeds R over 39, this can happen in one of two ways. Certainly, this event will occur if the future time exceeds 39 R days. This is the event on the right of the equation. It can also happen if the future time lies between R over 39 and 39R. This is the event to the left of the equation. And therefore, all you've written down is the principle of additivity. We've broken down the event that the future time exceeds R over 39 into two disjoint pieces. The future time is between R over 39 and 39R, and the future time exceeds 39R. And the moment you write something like this down, we can immediately turn through our Copernican assumption and plug in, identifying with the future duration little s, the values R over 39 and 39R respectively. And now an elementary calculation shows that we get a number 0.95. In words, in this model, there's a 95% chance that the future existence of the phenomenon lies between R over 39 and 39 times R, given that the phenomenon has existed for little r days. Let's try one more example. What is the conditional probability that the future existence of the phenomenon is at least R over 3 and no more than 3R, given that the phenomenon has existed for little r days? Again, additivity allows us to write down in one fell swoop a decomposition. And now we plug in our Copernican assumption, churn through the algebra, and we find that the chance that the future existence of the phenomenon lies between R over 3 and 3R, given that the phenomenon has existed for r days, is 50%. Curiouser and curiouser. Of course, you might ask, how did I pick these strange numbers, r over 39 and 39r, r over 3 and 3r? Of course, the short answer is I chose those numbers because I knew what I was doing, and I wanted to get nice answers at the right, 95%, 50%. You could replace the bookend of these inequalities by other values. Try that and see what you get. Our conclusion from this is as follows. There is a 95% chance that a phenomenon will not persist for more than 39 times the elapsed duration of the phenomenon. There is a 50% chance that the phenomenon will be extinguished within 3 times the elapsed duration of the phenomenon. All right, what does this say? Well, let's go back to the pictures we had and the various eclectic phenomena I showed you and come up with some amusing consequences. God points out that assuming a 4,600-year existence for the Great Pyramid of Cheops, the pyramid will continue to fascinate and beguile, create wonder and intrigue for maybe another 180,000 years before it disappears into the sands of the desert. This with a 95% confidence. The existence of Homo sapiens is another phenomenon. Assuming a 200,000-year current history for the species, the Copernican Principle in this formulation says, if you multiply it by about 39 or 40, that it predicates the continued existence of the species, our species, for an additional about 8 million years, 7.8 million years, but who's counting, with a 95% confidence. And that after about 8 million years, the species quietly disappears, like the dodo, into the well of extinguished species. Oh, that's very sad. But God, whimsically, provides an out. He says, well, what if the species manages to leave the Earth's gravitational well and colonize other planets? Then you might be able to evade this 7.8 million year moratorium on existence. But wait. To leave the planet's surface would require space exploration. But space exploration is a modern phenomenon. It has been in existence for about 50 years or so. So, given that space exploration as a phenomenon has existed for 50 years, there is a 50% chance that we will not explore space after 150 years from now. And so, here's a tongue-in-cheek exhortation for colonizing space, for investing in the space program. Our future existence in this tongue-in-cheek model depends upon it. A word of caution would be wise here. The model assumptions are large and sweeping. We cannot cavalierly apply it willy-nilly all over the place. For example, it would be ridiculous to apply the Copernican principle to a non-Hegelian. The principle says that the longer a phenomenon has been in existence, the longer its projected future existence. 39 times R with a 95% confidence. 3 times R with a 50% confidence. But a non-Hegelian does not have much longer to live given the biological constraints on the species as we have them today. The Copernican principle would fail badly in such a context. Right. Now, what is manifest here is that in such a setting, the observation point is manifestly special. If you choose the observation point towards the end of a person's lifetime, then there is not much surviving life to come. Another example might be, for instance, a second-term president of the United States. If a president is in his 7th year, then that would, by the Copernican principle, predicate a fairly long future tenure, much longer than, say, a president in his 1st year. But this would again be a bad misreading and application of the principle. The rules of the game in the United States put a 2-term limit currently on presidents, so a president cannot serve for more than 8 years. So if you look at a president in the 7th year, there is very little time left in his or her presidency. But there are other settings where the principle might well seem to be approximately applicable. Could you think of something? In a modern context, how about a startup? Common experience tells us that startups are extinguished in large numbers very early. Very few startups survive more than a few years. But if a startup survives its teething pains, gets venture capital funding, starts to make a profit, builds on the profit and starts to create a larger enterprise, creates an IPO so it becomes public and becomes large, then suddenly you have something with staying power. So then you have something like, let's say, an international business machine, an IBM, maybe an Amazon.com, something which survives from a setting where companies were falling in droves in the early stages. A few survived. But the moment they survive and they become big, they tend to persist for a long time. Here's a setting where one could think of applying the Copernican principle, and surely there is ample data out there that we can test that principle on. For our purposes, the idea was, one, it was interesting, it's fun, it's amusing. It is a simple application of the Laplacian model of succession. To posit a probability model where it was not clear what the sample space was, but nonetheless useful and intriguing predictions arise out of the setting. For our purposes, we think of this as an application of the theorem of total probability.